So the molecular similarity searching, which we will be seeing now pertaining to the cheminformatics. So in cheminformatics, we have already seen that it is a field of information technology that uses the computer and computer programs to facilitate the collection, storage, analysis, and manipulation of large quantities of chemical data. It is large quantities of chemical data. We are using it. It is not possible by the human brain, or we have to document it in the form of physical documents also. It retrieval is very difficult. So we are using IT. But when the data is very complex and more we are feeding it, so the complexity will be further enhanced. We are already having proteins in the protein nucleic acid in the bioinformatics and chemical structures in the cheminformatics. So what making a biggest difference, we have already seen. The biggest difference is that in the nucleic acids of DNA or RNA and proteins, amino acids in the proteins, they are the sequence of repeated units. So even though they are complex and high molecular weight, than our API and ligands, which are general chemicals, which are following Lipinski law of 5. So it is repeated units making this little bit simple. But whereas in the chemical structures, they don't have any particular sequence. They don't have any repeated units. Any atom can present at any time to the next to the neighboring atom. So this is actually what the complexity adds in the cheminformatics. This data is very much mandatory for us to use in the other branches of our drug discovery also. So where we are going to use more easily thought of encompassing large number of concepts and techniques of this particular chemical structure data in the molecular similarity determination and quantitative structure activity relationships. We want to find out where the structure has to be memorized. And substructure search, we want to search a similarity of functional groups so that all we can categorize as one group. And automated molecular depiction. So we want to find with one file and finding its structure automatically by giving the chemical name or the line form of chemical. So encoding and decoding of a molecular structures, then only it is possible. We have to do the encryption process where we have to convert into a human readable form of chemical structure into digital form of the computer binary system. And again, we need to decode that binary system into human readable form. This is encoding and decoding. So 3D structural generation from the 2D and 0D. So there is no dimension in the line structure. We will see in the SMILE, there is no dimension. It is a single line data. And the confirmation generation, conformer generation, we want to see what the pocket which are having, and in the 3-dimensional array, what the functional groups placed where and which are required for the algorithm generation, ring perception, aromacity, or it is aliphatic nature, or isomers are present, or any isotopes are present. These are all the complex where we need to make the computer very keen to understand these small critical differences. So how it is possible to do to make our entire data converting into information in the computers by its usable form and get a knowledge so that we can put it in the action to have a drug discovery. This is what the journey of today. So the computer representation of the molecules, we can, how can we molecular structure can be stored in the computer? One is by the common name, like aspirin. This is what we are giving a common name. So we call it as a generic name. And we have the IUPAC structural name, it is different. Chemical structural name is different. And what we are seeing in the right side is a chemical structure of aspirin, acetyl salicylic acid. So IUPAC name is 2-acetoxybenzoic acid, and formula we are giving there, we are able to know number of atoms present in each. So we are able to see it. And we can represent the structure of the human readable form in the PNG file, GIF file, and we can generate unique number, so chemical abstract number, CAS number, uniquely generated, so that we can identify by giving a name, by giving a number to it by the identification purpose in the chemical purchase where we are having it. So this CAS number is going to help. File formats, we can have like a mole file, ChemDraw file, SMILE formats we can have. Similarly, it is also present. These are all above. We can see, we can understand little bit by the human eye. But there is another binary fingerprinting is in the binary system where it is representing whole structure as a 0, 1, 0, 1, 0, 1 like that. So how it will be stored when we want to have it used for the computation, modification, manipulation, and searching and comparison. Similarly, we are going to create a unique identifier so that each chemical, by giving any format, we can identify that. One want to retain the stereochemical information, whether it is a three-dimensional or isotopic or isomers, and stereochemical information we have to store. So because of this, our computer is having a multiple types of file representation. In annotating, notation of each chemical can be placed in different file formats. So what is this slide is representing the same. Now I will take the attendance of the present day. All of you put on your cameras on so that we can have a screenshot. Already 20 members are there. We can take the screenshot of it. All of you put your photo on. Cameras on. Before jumping into the topic, good. Okay, Kiran. So where are the remaining photos? I have seen only Ram. Kiran is there. Shiva. Roll number 54 is there. Okay. Okay, Sri. So remaining people. Okay, Abhinav. Good. So now we will see how this computer is having this complex data memorizing and giving us the result. So the structure of a molecule can be represented by the computer in the form of a graph. So the graph means it is containing collection of nodes and edges. Most of the times it takes anything, either if you want to see image identification of our face, it takes our eye and nose and the tip of the nose and between the eyebrows a point as a node. It will convert entire thing into the triangle. So because of the distances of these nodes and the length of these edges, it will identify myself with my student and myself with my son. It will identify cat with tiger, even though kitten with small differences are also, it will be able to tell by the because of this graphical representation. Similar one, it is not going to make a mistake by doing like this. Because of this reason, we are having the structural data which is present. One form of representation is by the graph. Collection of the nodes and edges. Nodes and edges have the properties. So what are the properties? Atomic number, bond order, whether it is a how much is the distance is present, single bond, double bond, triple bond. So they represent the molecular graph somehow, the connection table. It will be giving the nodes connected with each other, how is connected with another one, what is the adjacent atom is present. This is one way it is present. Another one is a line notation. This is a simple form of making a line notation. Is a entire atom which is having a branches also. It is having rings also, presenting in the form of line, single line. That is called as a smile. So this is what the computer is doing. And we are having nearly 90 chemical file formats. So it is beyond our scope to learn all the 90 chemical file formats. And one software is called as OpenBabel. This software, it will convert each file format into other. If you feed one, it will convert into other. It is a freeware, we can convert. But what is interested and most preferably we use in our drug discovery many times is one is mole format, another is PDB files, protein database files, and mol2 files. And we are having a line notations for the, it is actually 0 dimension. Line notation is a 0 dimension. That is smile format. And in key also it is present in key, we have IN, that is international, CH is a chemical, I is a identifier format. So in Chi, we can follow whatever the one you want to have it, or international chemical identifier format. These are all the line notation. They are called as the 0D structures, 0 dimension. Whereas we have got a 2 dimension and 3 dimensions also. 2 dimensions, we will be having left and right, top and bottom. That is 2 dimension. And in the 3 dimension, we have got the depth also. 3 dimensional structure, which will be having a depth also. So 0 dimension, smile file, in Chi format. Another 2 dimension, we are having a mole format, and 3 dimension, we have got a PDB files. So we are having the different representation of the same moiety by the different file formats, which is allowing us to use for the separate purposes. We want to use for the comparison. We want to find the similarity of the atoms. Like that, we are going to have many utilities. So by using these file formats, for this purpose, 90 chemical formats are being used in our research community. So most preferably what we use them. So one is such is the line format. First we will be seeing. One is we are having the line format. If you see it, the commonly used line notations for the chemical structure is the smiles. The second is the international chemical identifier. First, we will start with this. So how it is having a computer, how we have drawn the boundary to name it. So we have got 2 types which are having in the international chemical identifiers also. We will see a little bit later. So in the SMILE specification rule, the first rule is a representation of the atoms. The first rule is representation of the atoms. So by doing like this, we can know the structure of compound without having, say, for example, we are giving a chemical abstract number, we are designating as a single number. But seeing that number, we don't have any information about what atom it is present in that chemical. That is not good. But in the SMILE format, one way of seeing is, we know the atoms, what are the atoms present in that chemical. So we can know that. That is the reason CAS number, we cannot use it in the our structure determination and property assignment. So these are all the things which we cannot use it. So that is the reason we represent atoms as such, like that only. So carbon is by C, nitrogen by N, O, oxygen, P. These are all the rules. So that is the first rule, is representing the atoms. So the second letter of the 2 characteristic atom must be in the lower case. Say, for example, in the case of the chlorine, C, we cannot give as a chlorine C because it is already been assigned to carbon. So in the atom notation, we are having a second letter that is in the small, where we are calling it as a chlorine, and Br for the bromine. So we cannot name chlorine as a 2 capital letter Cl. Otherwise, it will confuse with carbon and another letter L, that is another atom. So it is a chlorine. That is the reason. Atom notation in the SMILE file, the specification first rule is, first you need to give a number. If the same alphabet is appearing in the another atom in the periodic table, we have to use the second letter. That letter should be in the lower case. This is one. Each non-hydrogen atom is enclosed in the square bracket. Each non-hydrogen atom, it means we are having an iron hydrogen atom, means except nitrogen atom, is enclosed in the square brackets, like iron and that is gold. We are going to have like this. We are representing the square brackets. So this is first rule, which is giving the clarity. Now we are having the square brackets can be omitted for the elements in the organic subset if the proper number of the implicit hydrogens are already assumed. So we can omit the number of that is hydrogens which are present. It means we need not write if it is all orbitals are filled with of carbon is filled with 4 hydrogens. It is methane. You need not write. It is C. It is representing in the line. It is representing and one end of the starting of your chemical structure. If C is present, means it is remaining all is hydrogens only. No need to write that hydrogen atoms. So you have to represent non-hydrogen atoms only. Now you get the question little bit later. If it is not a methane, it is a methyl group CH3. Then we need to annotate it. There is no other option. If it is completely the valence atoms are filled with hydrogen, no need to write the number of hydrogen. We know it. So the proper number of the implicit hydrogen is assumed and we need not write it. So CH4, if it is present, that can be represented as N. Mi ammonia, that is NH3, can be represented as a NH2O. It is represented as a O. This is what the SMILE format it will tell. Don't get confused with another format. Now we are talking about only SMILE format. I am not entering into now international chemical identifier. There is a different rule there. We will see what is the difference there a little bit later. That is the reason directly I jump to SMILE format. Similarly, the atom explicit atoms or the formal charges are always specified inside the bracket if they are having a different valence states. So methyl group is represented as a CH3 within brackets, whereas CH4 will be represented as only C. This is what we need to have. So once we go to example, then we will come to know how this SMILE format is representing. BH2, we have to write NH4. This is quaternary ammonium state of ammonia. That is NH4 within the square bracket. So OH3 we are giving. Now it is representing going out of H2O water. And OH, that is hydroxyl group, we are giving. Similarly, we are giving the charge also there. So where we are having deteriorated water, so we are giving. Similarly, different valence states of ferric and ferrous. Ferrous can be represented as a Fe plus, that is charge 2, and R we can represent it as a plus plus in the SMILE notation. So this is where we are representing the atoms. Now the second rule in the SMILE format is bond. So atoms are containing bonds between them so that they will be getting attached to represent as a molecule. So this is what the PubChem is using, and these are the standard rules. And I am showing is what the PubChem is using, because it is not a public or open source. It is proprietary. The SMILE format is a proprietary in nature. In our GRCP, we can write one SMILE format. In University of Hyderabad, somebody can write it. It is a proprietary one. So we cannot say that, why are you writing like that? It is a major understanding between you and me. We can write it. This is the SMILE format. That is a primitive what we have got. The second rule in the SMILE format is bonds. Representing of atoms we have seen. Now we are representing the bonds. Single bond is written as 1 dash. And double bond is like 2 hyphens, that is equal to. And in our keyboard, we don't have anything to represent triple bond. Sir, I can put plus or minus one symbol is there like that. It is not present. That is the reason it is given as a hash. So triple bond is given. Wherever the hash is present means between the 2 atoms means the 2 atoms are joined by the triple bond. So 2 hyphens are present, 2 bars are present. That is double bond. Single bond is one. So the single bond can be omitted. If it is not present, means it is containing single bond only. Similarly, what we have omitted hydrogens, similarly we can omit it also. Now, aromatic bonds, which can be given as a dot, or it can be omitted. If it is not present, means it is aromatic bond. Now you see methane is represented as a C. Ethane is represented as a CC, or you can write as a C-C. We want to represent the single bond. So ethene is represented as single bond C. Ethine is represented as CH3, and acetone COC. And now you see we are taking ethanol CC, because C means it is containing remaining all our hydrogen. We can omit hydrogens. So the second carbon, it is having 2 hydrogens. We can omit it because by default we know it. And hydroxyl group, one bond is attached to the carbon, another carbon is hydrogen. So we can omit hydrogens. So CCO. Now you see the difference between this acetaldehyde and ethanol. CC double bond O here. So double bond O means H is not there. It is a ketone, what we have got here. So similarly, triple bond is represented as CHN. So if it is present in the one functional group, then we need to represent within the brackets, because H is not present. So that we are going to represent within the brackets. Hydrogen, we have not omitted it. If it is omitted, means we are thinking that it is containing hydrogen. So hydrogen cyanide, if a cyanide bond is present with any another aromatic ring or aliphatic, then we are going to represent like in the square brackets. This is the second rule of a smile. So that is representing the bonds. Now the third one is branching. So we are representing the branch. Sir, how we represent branches? So it is specified by the enclosures in the parenthesis. Next to it, we need to put as a not brackets. It is parenthesis. You have to not like a square brackets. We are having a normal brackets. We are having here. So if you see what you have got, one branching is present in the first structure in the left side. CC. In the second carbon, we have got a branching of methyl group, that is a C. And after that, we have got one more CH2, that is represented as wine. Ultimately, at the end, we have got a this is isobutyl alcohol, what we are representing. Similarly, the second structure, you have got a multiple branches and multiple. It is having a continuously, which is having a branches. So if you are staking whatever the line format in starting with 1C, or you want to start with nitrogen when the left, or right, or nitrogen in the left, you will have a different smile formats for this particular branching what you have seen here. It means the same compound, if you are taking from one carbon, what is representing in this particular case is methyl group is you are starting, then you are starting with a branching. Then you are going further and you are having the amide group. So like that, somebody else will be, which is the reason this smile format system is not uniquely having one smile file for one chemical. It is having a multiple smile files representation for the same chemical. This is the major problem. When you are coming to the branching, it is a little bit, because it is not a public one and it is a proprietary. Each company or each organization, they can notate as they like as a SOP, standard operating procedure. So when you want to represent the smile files, but the computer will understand all the combinations will be given to the same structure. It will understand, no problem. So it will be representing, say we are having similarity of all these names to the assigned to the one chemical structure. It will be done by the computer without any problem. Now the fourth rule for the smile is rings. Whenever you are coming to the ring systems, you are having aliphatic ring system and aromatic ring systems. So whenever you are representing the ring, it is a two-dimensional, it will happen. Ring will be having a left side or top and bottom, you are having a two-dimension. But line format, what you are using is a zero dimension. So you have to break the ring in the fourth rule of SMILE. You have to break the ring and represent in the line format. So benzene is represented as a C1 double bond C, single bond C, double bond C, single bond C, double bond C1. So where we are breaking, so the C1 is the connecting point that we will be knowing, and it is giving it as a benzene. So most of the times, the lower letters represent the aromaticity. That is the reason we have to represent the benzene as a small C1, C1. This is actually what the benzene is. If it is cyclohexane, you need to write capital C1, C1. It means all lowercase letters wherever we are present in the SMILE file, it is representing the aromatic ring system. Capital letters which are present, it is giving the aliphatic ring systems. Aliphatic atoms, they are the aliphatic atoms. Aromaticity will be represented by the small case letters. So ring system, it is now if you see the toluene, you will be having a multiple types of representation. Here we have got 7 types of representation can be done by the fall. All are canonical. It is scientifically approved. It can be proved. All of them according to the our branching system and rule 4, all rules which we have taken, all 7 representation will follow these SMILEs. It means multiple SMILEs represent the existing given molecule toluene. It is present. So this is actually what you may be having in the mind, that it is adding confusion to us also, and computer also may get confused. And but the computer has got a notation which I have already trained it. It will clarify that all these are all representing toluene, but it is adding something that it is not unique. Each file system in the SMILE is not unique. Now coming to the next problem and how to deal with the SMILE data is isomers, isomeric SMILEs. So isomers will be having the similar structure, but they are having the different, maybe having cis trans, dextro levo, or it may be R and S forms. They are all the differences you will be having it. How to represent in the SMILE format? First one is the isotope. Whenever there is an isotope which is present, carbon 12 is not present, it is existing generally. If it is having a radioactive methane, we want to use it, then you have to write that radioactive compound with its atomic weight of actual what it is present. So it is C13. So within brackets, we need to write. So we cannot write simply C now. In this particular case, we are writing within bracket 13CH4. It is for the isotope. The integral atomic mass preceding the atom symbol, we have to represent. In the stereochemistry, how we will get a naming a SMILEs file? Because in the stereochemistry, we are having up and downs, cis trans isomers, we have got a levo rotatory, dextro rotatory, structure is same. So how to represent in the SMILE format? Most of the times, which we are going to have, the one which we are going to have is L-alanine. If you are seeing it, it is having a L. We are having 2 ash, which is present in the carbon atom. Wherever it is present, 2 ashes. It is levorotatory. The same representing the R also, R configuration also. If you want to represent as R configuration also, it is present. So in the case of R configuration, we are representing the 2 ash. In the place where you have got a asymmetric carbon atom, it is having 2 ashes, means it is a R configuration. 1 ash means it is S configuration. Whereas if you want to have a L-alanine, which is having naturally abundant, which is represented by the 2 ash, D-alanine is non-natural alanine, which is represented as a single ash. Similarly, cis trans isomers, you have to represent cis trans isomers either by the reverse hash slashes which are present. So we can represent cis trans isomerism for the difluoroethane. Difluoroethane 1, 2. No, you want to have difluoroethane, hydrogen and fluorine is shared on the same side cis or the opposite sides trans. So we can represent by the reverse ashes. So what you are having the ash, what we are giving in the cis trans isomers, trans isomer, which is represented by the E form, and the cis isomer represented by the Z form. Where if you see the representation, C double bond C is same. So backward dash and normal slash, that is only the differences. We can make a differences. So we are able to make a separate unique atoms, and we are having a bondings, we are having a rings, which are having isomers. With all this, but only the rings we are breaking it, we are representing with where we are breaking it, we are representing in the line format. Now, what is the major limitation of this representation? We are able to, any molecule, we are able to convert it. What is the limitation of this? Most smiles encode decays are proprietary. It is not used by the universally. Because why it is proprietary, we have got a some number of notations. It is based on their interest, they can notate as they like. So that is having one thing. That is the reason different groups implemented slightly different smile generation algorithms. That is making a little bit confusion in the complex Clearly, we have got not interchangeable between the databases. Small research group you can use unless the same software is used. We can transfer one file to one place and one software using the smiles data. But the smile format has got limitation because some chemicals will be represented n number of smile files. So that confusion will be present. Open smiles were developed. Lens, don't name toluene like this. You have to name like this only. That is called as open smiles. Everybody has to follow it, but people are not following because they have got their own interest to name according to their SOP what the company says. They have to follow that only. So this type of smiles has got this problem. Chemical CH, I, in-Chi system has came into the existence. So because, my dear people, we are all contributing to the world, our knowledge. You are representing in a different smile format, and we want to give a open smile format also. It is difficult to follow and not following. So IUPAC made a entire world. We have to follow this in-Chi system, originally developed by the IUPAC. Continuing development efforts by the in-Chi Trust, they made the efforts to make all they are uniquely numbered, not having a different file formats, different files for the same chemical. That is actually what they are doing. So it is non-proprietary, it is not present in hands of any owner, and it is open source and freely available. Everybody will follow it. So this in-Chi string generator is also freely available. Avoid the interoperability issues of the smile. Any software can use it because it is universally accepted it. So say for example, we are having ATM cards. ATM card size is same throughout the world. Say for example, if you want to in your company, just like a smile format, you are writing an SOP, you are creating own money dispensing machine and own card. The size can be same fit, it will be generating and giving the result, and you can operate and you can get the money in your own organization, but you cannot operate anywhere in the world. This is what the problem with Smile, that is proprietary software. Whereas this open source software, it is open everywhere. It is having a similar format, a similar dimension. That is the reason it is superior over Smile file. That is in-Chi file is a superior. That is how we have got an advancement in the CAD. This has resulted into the so much of advancement. And in this particular case, in-Chi system, how we are representing the methane. So generally, we are having a standard and non-standard format. In any methane, the standard methane is not containing any isotopes. that is C13 is not present. So they randomly present all. So these are all the standard formats. That is represented by the 1s and CH4, and it is representing the number of hydrogens are present, and the number of bonds are present to the adjacent to one hydrogen, number of hard bonds are present. Like that, the computer is generating the file, INCAI file, to each one that is uniquely present. That is uniquely present. INCAI, we will have this specification for the INCAI also. There is separate PPT, and we will see that also in the nearby subsequent slide. We will come to know how it is having. So this INCAI encodes the chemical structure into the layers. The first is, it is a standard or non-standard. That is the one which is going to give. Separated by the forward slashes. It is not the backward slashes. We have got used the slashes in the cis-trans isomerism there in the smile format. Now we are having all forward slashes only in this particular smile. So we are going to have the L-alanine, what we have seen in the one is different. Now what you are got here, it is different. It is having a number of characteristics, number of letters are more in this particular INCAI system. If you see it carefully, you will find the difference. So INCAI encodes the structural into the layers. So the first layer, it will be the standard non-isotopic and it is standard format. Then it will give the number of each atom, how many atoms are present, how many numbers are present. That will give. So it is so good to know that the chemical formula, what we are getting, you are giving that one as a second slash, forward slash. Each layer has the different, that is distinct and separable class of the chemical structural information. So the main layer is a chemical formula, and that is standard or not standard. And there is a number atoms. Then it has got the bonds. So then it have got another layer like for the charge layer, and it will have another layer slash, that is forward slash for the stereochemical layer. And it will have another slash like isotopic layer in particular case where you are having non-standard. In the non-standard, in the first letter N, in the place of S, you will have a N. You will have isotopic layer. Where it is non-standard, it is present, it will have a show in the which atom is having isotopic in nature. That layer will be present. And fixed H layer and reconnector layers. These are all, so many layers are created by the computer system. It is recommended and operated by the IUPAC, and we can generally use it. So INCAI is not easy for the human to understand, especially compared to the smile string. What we have seen previously, it is easy, but it is so complex here. There are so many forward slashes are present and bonds are there. Number it is giving first layer, it is we are able to understand easily because it is containing number of atoms like that. But it is not as easy that of smiles. It is not easy for the human to understand. It is because INCAI was developed as a machine-readable chemical identifier with the aim to regenerate and corresponding chemical structure from the INCAI string generated by the another computer. So that is the reason. It is for the machine learning purpose we have to use this. For human learning purpose, transferring into a simple line by just typing it in the keyboard, we have used the smile data without using any JPG files formats. So we want to convert a structure into a Word document. In the smile, what we are doing, we are not using any JPG. We are not drawing any lines. Just we are writing as a doc only. And we can type it also. And even in the triple bond, we are typing as a hash. But here we are doing the same thing. But it is difficult to understand in the line diagram what we are representing is a reasonable form. We are having a difficulty. So what are the difficulties which we have got further rectified by the INCAI key systems? Because we are having, you see here in the INCAI, what you have got is having so many number of letters. Sometimes it will be having 2-3 slides. One INCAI file will be having a 2-3 files data. That much you will be having. So now what is there? IUPAC has done one key system. One that key that will open so many things and helpful to us for the identification. At this juncture, we will take again our attendance. Open your cameras on. Switch on your cameras. Good. Kiran. I'm taking print screens of all. We are opening it. If somebody is not responding, either they need to put it in the chat that what their problem is. Chandan has already kept. So somebody is keeping the problem. You have to keep in the chat, or you have to put it in my WhatsApp now only, not later. Okay. Roll number 54. Six, camera issue. Okay. Yeah. Abhinav. Okay. Any queries at this particular one? We have got the smiles and we have seen in-case system. So international identifier, INCHI. Now we are entering into the third type of format and more modification. Now it is being used is in-key key. In-key key, that is INCHI-KEY, in-key system. So we will enter and wind up the introduce that one, and we will see remaining 5 types and how to make molecular similarity structures tomorrow. So in the in-key, that is INCHI-KEY format, the it is all chemicals are represented by the 27 characters. Any chemical which will be represented as a 27 characters. So in this particular, the first 14 characters in the in-key system, which is having the molecular skeleton and connectivity. Then after 14 characters of the in-key file, that is file format, you will have a hyphen. Then you will have 8 characters. That will give the stereochemistry, isotopes, and tautomerism. So now we are having how many? 22 are present. So now we are in the first 14 plus 8 characters which are having. So now we are having furthermore, so which is representing the last one is the proteination and deproteination, which we are having the characters. And we have got in between hyphen also. That hyphen is also considered as a one character. So they are separated by the characters and hyphens and characters, and each one which is having, so in the in-case system format, it is having the 14 characters silicon, that is one more hyphen, 8 character stereochemistry, that is including your isotopes, tautomerisms, and cis strands, levodextro, R and X, all before above the plane of paper and below the rotating plane of polarized type to left and right. Based on the what its characteristic is. Another one is keto-enol tautomerism, where we are having a enol group, He can be removed. In the keto group, H is locked. So keto-enol tautomerism, where we are having same structure, but it is different way of behaving according to the environment. So we are going to represent the same thing in the 8 characteristics. So then you have got F. That is next character hyphen. We are having standard and non-standard flags. Standard flag is S and non-standard structure flag N. And the version, now what we are having the version A is 1. And the final letter after hyphen is the character is for the proteinated state. So proteinated states of that particular molecule represented by the 5 letters N, P, O, N, M, O, P, Q. N, M, O, P, Q. N for the neutral, no protonation, no deprotonation. -1 is proton deprotonated. It is having a electron acceptor, that is a proton acceptor group. So O is for single proton protonated. P for 2 protons are present. Q for the lacking in 2 protons, the deprotonated states. So like that, it is representing the final state in the final letter. Together in the 27 characters, whatever the moiety you take it, it will be represented in the in-key system. It means it is so unique. So combination what we have got this 14 characters, you can create crores and crores of structures in the same characteristics what we are giving it. So computer will assign and understand what the chemical nature is. This is what the in-key system will be present. So the palytoxin, what you say as an example, which is present as a structure now, if you are observing on the scheme, it is one of the most toxic non-protein substances known, second only to the mycotoxin in terms of the toxicity in the mice. Very big structure, you see, very complex structure, just like a protein links, it is having a multiple repeated units also present. So many things are present resembling your that proteomic data, but it is not a protein or a nucleic acid sequence. It is a chemical API only. What does the in-key string it is present for this compound? You see it. Oh my God, you see. How much is the one now? So complex is the in-key system, which is given. It will be represented with the 7-letter in-key system with the string for what you have got in-key like this. That the in-key system for this entire that is what you are representing in the in-key. We are going to convert this into key, that is 27 letters. This entire thing into yes 27 letter. So the length of in-key string increases with the size of the corresponding chemical structure, not appropriate to use for the internet algorithms, Yahoo, Bing, and so on. These structure engineers do not care for the sensitivity of the in-key. That is the reason we are converting into in-key. Key was introduced, INCHI-KEY, key, because it is a 27 characters. So what you are having in this particular case, we are going to have all are having a 27 characters string derived from the in-key that is containing pages using the hash algorithm. Hash algorithm means one particular set will be hashed for with one letter like that. It is fixed there, hash algorithm, which is present. And hashing is one way of mathematical transformation of typically used to calculate the compact, the fixed length digital representation of a much stronger string into arbitrary length by representing. It is not possible to reconstruct the chemical from the in-key, but we can construct the in-key from the chemical because of this particular hashing. So this is actually what the one way of representing, but still it is also a complex. It is a complex phenomena where we are not able to get in the human readable form. So in the smile notation, in-key notation, in-key key notation, smile is for the good readable for the human readable form. So now you see for the what you have got the toxin, it is much simpler, but it contains no human form. What the representation is 27-letter code. In-key file is having so many letters plus 86 MO/S1. It is starting with in-key 1S. That is a standard. It is not having any isotopes. So this is all the thing is this in-key system is having much help with representation with the number of letters small, and it is unique present. So it is not the vice versa. This cannot code, we cannot go back to in-key structure from the in-key to the structure, but we can create structure from the in-key. It is much simpler, but it contains a non-readable format. Now we will be coming to the computer-aided drug design, how we are going to use these files and further file formats for the using in the CAD. Tomorrow we'll see. If anybody is having a doubt, now floor is open for the discussion. Somebody has written camera issue 106.